Hi, I'm Gary, and I want to show you how I use Cloudy. We've been talking about the cooling function and how the spectrum changes as the metallicity changes. So we saw two pretty amazing things in both figures shown here. We changed the metallicity between 1% of solar down up to 10 times solar. For much of the range, the 5.007 H beta ratio, the oxygen to hydrogen ratio, changes by about a factor of two, despite the oxygen changing by several orders of magnitude relative to hydrogen. And that was because of the thermostat effect. The heating was set by the starlight, that's constant. As you increase the metallicity, the cooling efficiency of the gas increases because the cooling is mostly corrosion excitation of forbidden lines. The cooling goes up, so the gas temperature has to go down because the cooling has to equal the heating. So this is the thermostat effect. What we're going to do now is look at some spectra at various metallicities in this plot we just saw. And we're going to look at 0.01% solar up to 10 times solar. And this is the input script that's going to do it. So here we're varying the metallicity between 1%, 10 to the minus 2, and 10 times solar in one dex steps. We were going to save the spectrum at each one of these models and have a look. There's a problem. It's a heads up. Uh, Cloudy stops when the temperature falls below 4,000 degrees to avoid that inflection in the cooling function that starts at around 4,000 degrees. And when we get to high metallicities, when we get to 5 or 10 times solar, the gas temperature is going to be about room temperature. It'd be 500 degrees or so. And so Cloudy, if you don't tell it something special, will do one zone, find a low temperature and quit. So it's not going to do the full H2 region. So the purpose here is we want to make a model. You see the title. We want to make a model of a whole H2 region going from the illuminated phase to the ionization front. So there's two things we have to do to get Cloudy to behave. First of all, we have to turn off the temperature stop criteria. So the stop temperature allows you to change the lowest temperature allowed, and we're just going to turn it off. So if we do that, we have to tell Cloudy why we do want to stop, else it'll just keep going. We want to stop at the hydrogen ionization front. So there's a trick to do that with this efrac command. And so this efrac is the electron fraction, the number of electrons divided by total number of hydrogens. This says stop when this ratio is less than 0.1 or 10%. So that should be well into the hydrogen ionization front. So with these two commands, no matter how cold the gas gets, we'll get to the hydrogen ionization front. The other thing we're going to do is save as separate files the spectrum at each one of these models. So this has a separate command that means don't do the gather at the end to bring the grid points back together into one file. We want to make separate plots. Now there's a heads up for how the save continuum separate command works is you expect to get a column row at the very beginning. So this is the first one of the save spectrum files. So this is the expected title. The command is set up so it's expecting just to do a large run of different spectra files all in the same file, so it only has one title row. And so the other spectrum files, the first one is going to have the title row, the other one will be missing it, so we'll just add it so Views knows what to do. So with that, we can then look at the spectrum, the optical near IR spectrum seen at these very, very different metallicities. So this is the kind of plot we're going to look at. I'm going to keep it exactly the same so we can blink back and forth between various metallicities. This is the 1% of solar case. So the optical is in this part of the spectrum here, and this goes from a millimeter down to the FUV. It goes below the Lyman limit. And I'll keep the vertical scale the same too. So this is the Balmer continuum. You can see it's going up to the Lyman jump here. You can figure out what these different lines are. This is helium-1 Lyman alpha in the FUV. This is hydrogen Lyman alpha. This is Balmer alpha. So there are some forbidden lines down here, but mostly it's the gas is cooling by free bound emission and still making phenol-7, making the optical lines, despite the very, very low abundance of oxygen, because the gas temperature is so high. This gas is up at 20,000 Kelvin. So we can go to 10 times higher metallicity. Now we can go to 1/10 of solar. So you can see some additional lines are present. So these are the forbidden lines of the heavy elements are coming in. So the gas temperature goes down because now we have extra cooling lines. Heating equals cooling. And actually get some lines in the infrared. Just to have another look at that, 1%, 10%. We can next go up to solar. There's 10%. Here's solar. So you can see the spectrum changed quite a bit. There's a lot more in the infrared. The temperature has come down, so the UV lines are suppressed by the Boltzmann factor. It's not, the gas isn't hot enough to excite into UV, but it's plenty warm to excite in the infrared. So go back to 1/10 of solar, very weak lines in the infrared to solar. So the temperature is now at solar, I believe, is about 8,000 Kelvin or so. And then take the last leap going up to 10 times solar. So the temperature is going to fall down to around room temperature and see what that looks like. So you can see it doesn't look dramatic, but you can see the lines in the infrared are about 3 or 4 times stronger than they were before. So 10 times solar. So the forbidden lines are getting stronger, and the cooling has shifted into the far infrared. What does the spectrum look like, you may ask? We can do that. So we just make a spectrum of a single optical region for the highest metallicity that we did. So this is the full optical spectrum seen in great detail. So we have mainly recombination lines. This is a recombination line spectrum. So this is Balmer alpha going on down the Balmer series. Here's the Balmer jump. Here's the Passion jump, very strong. And here's the Balmer lines. The Balmer jump and the Passion jump are very sharp. This width here is very sharp. And so these represent electrons from the thermal energy band above the ionization limit. So the width of this Balmer jump is how how wide the free electrons are. So they're all bunched up right at the continuum because the gas is so cold. The free electrons have very little energy. So the Balmer jump looks very sharp, the Passion jump too. This is not seen in H2 regions, to the best of my knowledge. This does not look like the spectrum of an H2 region, but it is seen. It was discovered in 1978 by Bob Williams, who had become a program of looking at shells around old novae. So novae is gas ejected from white dwarfs. My PhD thesis was on a nova B1500 Cygni. And Bob found, when he looked at the nova that exploded in 1934, the shell of gas was visible like a nebula in the sky, that it was indeed down around room temperature. So this is that very, very sharp Balmer jump, and there's no forbidden lines. And so what's happening in this nova, because it came off a white dwarf, it's super enriched in heavy elements, and it's found these solutions down at low temperature. So they occur in nature, but they don't appear to occur in galaxies in H2 regions. Why? Generally, nature will do anything that's not explicitly forbidden. So I'll ask one other question like this. This was the video 20 cooling function. The gray areas are the stable regions, so the gas is allowed. So this is the molecular clouds, PDRs. This is the H2 regions, planetary nebulae, supernova remnants, the interstellar medium. This is very hot gas, so this would be the shocked bubble around star clusters in H2 regions or in nebulae. But then there's lots of examples of this. So we see these three phases all the time, but to the best of my knowledge, we never see gas up here. So let's ask what would it look like. So set up a simple model to do a constant temperature model at 50,000 Kelvin, which is about the middle of that band, and then have a look at the emitted spectrum. So the spectrum is quite unlike anything anybody's ever seen. If someone saw this spectrum, they would aim it towards nature or after letters or something like that. It's the lines are all middling. It's not just 507 sticking up. 507 is probably in there somewhere, but there's a lot of lines. This gas is very hot, and it's able to excite a lot of lines that you don't normally see. And so, for whatever reason, we got nature likes to populate these three bands. We don't have any examples that I know of this band. You'd only speculate it's because this said to be it's fairly fine-tuned. The range of heating to end up here is less than 10, whereas the range of heating for these other bands is many orders of magnitude. And then the gas over here is nowhere else to go. It's trapped. So the question just to leave this is where are they? Where are the high metallicity, high being 5, H2 regions? There's no place in the universe where the metallicity has gotten that high, apparently. And where's the gas up at the fourth stable phase that ought to be around? Okay, next time we're going to combine these ideas and see how it is we can say something about the SED, the spectral energy distribution of the incident radiation field, the starlight that photoionized the cloud. So see you then.